Hello, you're welcome. All right, so we are going to be talking about logic gate in this video. All right, what is a logic gate? Of course, logic gate is the gate where logic decision is made in a digital system. All right. Now, every digital system actually have a processor, right? That processes information based on the input that is actually fed to the processor. Now, you are very familiar with this, with a computer system and, of course, the architecture of a computer. So now look at a logic gate as one of the components, all right, or perhaps the smallest component of a processor in a computer system, all right. So that simply means that a processor that processes a large information is made up of thousands or even millions of logic gates combining together to um, execute a task or to execute complex task. Okay, so the complex task that is executed by a processor or a microprocessor, all right, can actually be traced to a simple logic gate, which of course we are going to be looking at in this particular video. So let's look at different logic gates that actually perform simple tasks. First of all, let's start with uh, the OR gate. Now, this logic gate, of course, is known as the logical addition. Now, this is the symbol. Each of the logic gates, I'm gonna actually illustrate the logic gate by the symbol. Of course, I'm gonna draw the symbol. All right. So it is a logical addition OR gate. It takes two input and of course produce the logical addition of those two inputs. So the output is C. All right. So now different combination of the input will give us a specified output, which we're going to see in the truth table. So the truth table is going to show us the output based on different combination of the input. All right. A, B is the input, while C is the output. Now, when A is low, that is 0, B is 0, okay? That simply means that 0 plus 0 will give 0. Logical addition of 0 plus 0 will give us 0. If A happens to be 1, and of course B is 0, 1 plus 0 is 1, 1 plus 1 will give us 1. So invariably, in logical addition or in OR gate, the only time we are going to have low, all right, the only time the output is low or the output is 0 is when the two input is 0. But if the two input is not 0, okay, then we definitely will have 1 as our output, or even one if one of the input or both input, right, are 0, we definitely have 1. So we only have just one time or one combination that will give us low, okay, that will give us a low output. So please take note of that. So we call this is this actually is OR gate, and this is the symbol. Take note of the symbol. Now let's look at the AND gate. This is logical uh, okay, product or multiplication. It's a dot product, okay. So A dot B. Now this is the symbol. It takes two inputs and of course delivers one output. So let's look at the truth table. The input A and of course B, then of course we'll have the output. Let's look at different combination. Let's start with when A is 0 and B is 0. 0 dot 0 or 0 times 0 will give us 0. Anything you multiply by 0 is always 0. Take note. Even if this one of the inputs is 1 and the other is 0, 0 times 1 we end up giving us 0. What if This is 0, and of course the second is 1. Please pardon me. This is 0, please. We end up giving us 0. What if this is 0 and this is 1? I still have 0. So invariably for the AND gate is the opposite of the OR gate. The output will be 0 in as much as one input is 0. Okay. The only time you have the output becomes 1 is when the two inputs is actually 1. That is when you will have that. Okay. So please take note of this. Okay, so this is the symbol. Now let's look at another gate known as the NOT gate. NOT gate. This, of course, is a logical complement. What is a complement? A complement is an invert or inverse of the input. Alright, that simply means that if the input is 1, a complement of the input will be 0. And if the input is 0, the complement of the input will be 1. So invariably this is how we represent that, okay, with a bubble. So the same way it is a logical, this is a logical complement. So if it takes in an input A, then the output is going to be the complement of the input A bar or A prime. Alright, anyhow you want to represent it. So if A happens to be 1, then A bar is 0. If A is 0, then A bar is 1. Logical complement. The next gate we are going to look at is known as the SOR gate. This is an exclusive OR. That's what it means. Exclusive OR. It's an OR gate, but it's an exclusive OR gate. Look at the symbol. The symbol is almost the same symbol with an OR gate, but there's just some slight, okay. This, once you see this included, of course, this is the symbol of XOR gate, and of course it's an exclusive also. If this is how we actually write the expression A XOR B. All right, that is the output. C is A XOR B. So this is the input A and this is B. So how do we actually define the truth table? What is the truth table of this gate? All right, so A, then B, output is C. Let's begin. Now for a XOR gate, the only time the input is 1 is when the output actually is when the output is actually different. Okay, if the output are the same, all right, sorry, the only time the output will be 1 if when the input are different. All right, when the input have a different value. But if the input are the same, then the output will be 0. Are you okay? So it is only when I have 1 here, 0, A is 1, B is 0, that I will have 1. Or A is 0 or B is 1, that's when you will have 1. But if it happen that both A and B is high, then definitely, so if A and B is low, output will be low. If A and B is high, output will be high. So that is the exclusive OR gate. The exclusive OR gate. I hope that is well understood. So let's look at the complement of all these gates. Remember, complement is simply an inverse of the input. Let's start with the complement of all gates, known as NOR gates. So NOR gates simply means not all. It is all, but all gates, then it is complemented. How do we write the symbol of NOR gates? Simply, we will write the symbol of the normal OR gate, then we complement the output by putting a bubble to the output. Okay? Okay. So this bubble at the output show that the output is being complemented. So this is the input A, input B. Then this is the output is A plus B, then it is being complemented. Not all. This is all. Then the bar on top means not all. Okay, so that simply means that I don't need to write the truth table of this. The truth table of this is still going to be the truth table of what we have, but it's complemented. So I can actually copy it. Please pardon me. Okay, I can actually copy this out. Then I add the complement of the output, and that will give us once I add the complement of the output, and we are good to go. Okay, so all you just need to do is this is all gates. Okay, here we have this C, so all gate. All right, then for me to actually add another column, I can add another column. Okay, so this column now becomes C complement, which of course is A plus B all complement. So what's going to be the output? So for C complement of 0 is 1. Okay, this is 0. This is 0. So this is 0. So the truth table of NOR gate is actually the opposite or the inverse of the OR gate. Okay, so all you just need to do, find the inverse of the output of the NOR gate of the OR gate, that will give you the output of the NOR gate. So it's just very simple. The logic is very simple. So you can actually write that. The same goes with the NAND gate. NAND gate. Okay, so this is, you know what it is? Not and. So in this case, we are still going to write the symbol. We draw the symbol of the AND gate. Okay, but we give it a bubble output. Input A and B. Then output C is A dot B, but the output is complemented. Okay, or better still, the output is A dot B complemented. Okay, the output is A dot B complemented. Complement. All right, so I'm very sure that you can actually draw the truth table of this. This is going to be the same truth table for the AND gate, but the output is complemented. So please take note of all this logic gates. So this is the foundation of complex digital system. All right, every digital system, all right, no matter how complex they are, actually originate from this simple logic gates. So we are going to be looking at more complex digital system and how we can simplify them into a very simple logic gate. All right. So that will bring us to what is known as the Boolean algebra. Okay. So we are going to look at Boolean algebra. In Boolean algebra, this is actually an algebra that helps us to simplify complex system, all right, or complex logical expression into, we simplify complex logical expression so that we can actually reduce the component that is used in building the digital system. That is what we are going to do in the next video. So see you in the next video. Thank you very much.